So now in second video, today we'll be going for conservation of angular momentum. So give the heading, conservation of angular momentum. Three conservations are very important. One, first we have done conservation of energy. Second, in center of mass we have done conservation of momentum. Now this is third conservation, that is conservation of angular momentum. And very important. And here how to start? Let's see. We have just proved that dl by dt is equal to torque external, or about given axis dl axis by dt is equal to t about that axis. Okay. So if I have taken system in such a way कि about a given point can be anywhere, point you have to choose point in such a way कि about that point if torque external is 0, okay, means let's say about a given point if external torque is 0, so it becomes what? To dl axis is 0. L axis, dl axis 0 means that implies L about that axis is constant, means L initial equal to L final, or you can do this integration also, L about that axis initially equal to L about that axis final. So I can write here I can write L about that axis final equal to L about that axis initial, and this is conservation of angular momentum. Okay, this is conservation of angular momentum, and very easy, very effective, very useful. जो अपना टॉपिक होगा ग्रेविटेशन, उसमें काफ़ी यूज़ में आएगा ये. So here यहाँ पे so what we have to do, we have to choose what? We have to choose a point about which torque on the system is 0. Which torque? Obviously external torque. Torque is because of external force. The external torque about the system is 0. About that point is very important, and this you have to choose, and that gets clear when you solve the question, so that is not a problem. So torque about a given point if it is 0, okay, so angular momentum about that point, if axis is passing through that point, so angular momentum about that axis, that point will be constant, conserved. This is conservation of angular momentum. And since we are doing first pure rotation, okay, so we are doing translation as well as rotation both. Pure, combine के लिए we'll see afterwards. So let's see, let's apply, then it will be more clear. Question है, let's start with a simple question. A disk of mass capital M, a disk of mass capital M and radius small r is rotating about its axis with angular velocity omega. Now if a mass small m falls vertically on its rim and sticks to it. Now if a mass small m falls vertically on its rim and sticks to it, then find the angular velocity of combined system. So find angular velocity of combined system. So what is the situation given? A disk is rotating, so there will be some axis. Let's say if its axis means it's a symmetrical axis, so about this is rotating, this is kept horizontal, but the disk is rotating like this. This is my disk, so disk is rotating like this, so disk is rotating like this, or the symmetrical axis. A mass m falls on the rim, so small mass m falls here. If dimension is not given of mass, so we have to take a point mass. So initially क्या है? Initially this is rotating about this with omega, and mass m falls. So m falls here. Nothing is given, so we'll take initial, means velocity of fall is 0. Okay, that we always take a simple case. So after falling, the second situation becomes this. So mass m falls here. So what is the new omega? That we have to find. And stick हो गया है, तो इस रिम पे ही वो घूमने लगा उसके साथ. So let's first of all, this question cannot, since it is a rotation, so this question cannot be solved by momentum. So let's see, first of all, what is my system? So system, in my system we have disk. Okay, in my system we have a disk and the mass small m. That is in my system. Okay, now you have to draw, so draw FBD for practice. So here डिस्क का मास यहाँ से पास होगा mg, एंड डिस्क यहाँ पे हिंज के तभी रोटेट हो रहा होगा, तो यहाँ से n विल बी फ्रॉम हियर n नॉट. ओके, यहाँ पे mg जब कांटेक्ट हुआ, तो कांटेक्ट के जस्ट पहले और जस्ट बाद यहाँ पे mg, and this will be again n, this will be n prime, and there is mg, capital Mg. This is my force. Now I have taken, now you can see, if you take disk and the small mass in your system, small mass collides with the disk. So during collision, which force acts? If you remember, it's an impulsive force. So if I draw separately, the force, let's say यहीं मैं draw कर रहा हूँ, डिस्क के लिए क्या हो जाएगा? It's mg, and there will be a normal contact force, or impulsive force, let's say n naught. Okay, and there will be n by the hinge about which disk is rotating. On small mass, this is going to be n naught. ये यहीं पे होगा, यहीं पे मैं ड्रॉ कर रहा हूँ. This is n naught, this is mg. Okay, collision जो हो रहा है, this collision is what? It is completely inelastic collision, correct? So I have taken disk and the small mass in my system. If I have taken both in my system, what will happen? If you just see, so what is the net external force on this? So if you remember, whenever collision takes place, we neglect the small forces. Whenever collision takes place, we neglect the small forces. Okay, so here mg can be neglected. Okay, so mg we can neglect this. Let me know green. Mg can be neglected. This mg can be also neglected. So on my system, n naught, the impulsive force during collision, is a internal force, but a force by hinge, because if on disk this n naught is impulsive, so hinge force n should be also impulsive, otherwise this disk will break. Okay, अगर disk यहाँ पे hinge किया हुआ है, यहाँ पे अगर impulsive force act हो रहा है, तो the hinge should also apply an impulsive force, otherwise disk will break. Disk is going to break. Okay, so on my system I have taken disk and the mass in my system. So this N is an impulsive force which cannot be neglected, and this N by the hinge, it's a external force, external impulsive force. So in this case you cannot apply momentum conservation. Getting this very important point. So what next? Next is energy conservation apply नहीं कर सकते because it's a inelastic collision. We don't know. So that is also gone. Momentum also gone. Left with angular momentum. Now let's choose a point. Now let's say hinge point is taken is the origin. About hinge point, I am calculating the torque. You have to choose a point, an axis, a point on the axis. That is important. A point on the axis about which the net external torque is 0. So since mg or this this mg is neglected, so you can see torque due to this n naught, the external means torque, this n is internal impulsive force. So torque due to this n and this n will cancel. Since I have taken disk and the small mass in my system, so this n naught becomes internal force. So internal force का torque क्या आ जाएगा? 0. mg is neglected because in comparison to n naught, mg is neglected. Okay, so torque due to this n naught is this way, this n naught this way, on small mass this way and disk this way, so the both will cancel each other about this point. Due to mg which already neglected, or if you don't neglect also, mg ka torque about O will be 0, and torque due to hinge force, impulsive hinge force n is also 0. So net torque about O is 0 after neglecting small mg, and that we can neglect because it's a collision, so we neglect the small forces. So we can see torque about O before and after collision is 0, and torque about O is 0 means what? Angular momentum is conserved. So we can write L about given L initial equal to L final about the axis. Axis is along this. Before collision, disk is rotating. For disk it is I into omega equal to, and plus its velocity is 0. Otherwise अगर इसका भी velocity होता तो इसका भी फिर angular momentum आता था about this. It's a point mass. तो क्या आता था? mvr. It's a point mass. Point mass is line of velocity. ये हो गया. So this is going to be the perpendicular distance. But since it is 0, so angular momentum of small mass before collision is 0. After collision क्या हो? Stick हो गया. तो I of the system into omega prime. And this is initial, this is final. Finally क्या है? Disk plus this mass. So for disk it is what? M r square by 2 into omega equal to I of system. क्या होगा? System includes disk, तो disk का होगा M and small mass. So that is M, I think small r, na? Small r, mr square by omega prime. So from here we can get omega prime is m, r square is cancelled. So m omega by 2 m plus m. This is the, just see, it's very easy example, very important, and how to visualize. Repeat करके 2-3 बार देखो, I think फिर समझेगा. Next question. Connected with this question only. Please write. In the previous question, if instead of particle a disk of mass capital M by 2, disk of mass capital M by 2 and radius small r is kept on the first one with axis coinciding, find final angular velocity of the system. Find final angular velocity of the system. What is given? The previous problem this disk is rotating again same, एंड इस पे एक दूसरा डिस्क मैंने रख दिया. मास रेडियस वही है, रेडियस मास इज m, रेडियस इज r. In second, just they have not mentioned the velocity, so we'll say कि they have just kept with zero velocity, and zero velocity है, so and its axis is coinciding. They have said this. So this is my first disk, and इस पे मैंने second disk मैंने रख दिया है. And that disk has coincided. ठीक है, तो this is my second disk which we have kept here. This mass is m by 2, radius is same, initial mass is m. Again, now see what are the forces drawn. जैसे स्टिक हो गया, मीनिंग व्हाट कि वी कैन नॉट डू एनर्जी कंजर्वेशन बिकॉज इट्स अ इनएलास्टिक कोलिजन. व्हाट अबाउट मोमेंटम कंजर्वेशन? मोमेंटम कंजर्वेशन आल्सो वी कैन नॉट डू. व्हाई? बिकॉज देयर इज अ हिंज फोर्स, एक्सटर्नल फोर्स. इफ आई टेक बोथ डिस्क इन माय सिस्टम, तो इंटरैक्टिव द इंपल्सिव फोर्स बिटवीन द डिस्क इज इंटरनल फोर्स, दैट इज ट्रू, बट द हिंज फोर्स विल बी एक्सटर्नल. तो जो हिंज फोर्स आएगा दैट will be external. Okay, so just before and after hinge force will be external, so we cannot apply momentum conservation. For both masses, mg will act from here itself. This is 3 mg by 2, m plus m by 2. So if I take again, we can neglect 3 mg by 2 in comparison to impulsive hinge force, that is n. Before keeping the disk is at rest. Okay, so before keeping the disk is slightly above, disk is here. Before keeping here, disk is at rest, and after keeping, disk will start rotating. They both have stick together. So let's say it starts rotating with omega prime. So about O, the net hinge impulsive force is 0. Impulsive force between the disk is an internal force because I have taken both in my system, so its torque is 0. mg can be neglected, or if you take due to 3 mg by 2, torque is also 0 because the mg is passing through the hinge point only. So we can do initial angular momentum I omega equal to I system into omega prime. Okay, since it's a pure rotation, तो angular momentum is I omega. तो initially for this is mr square by 2 small r into omega, plus second disk is not rotating, so it's 0. Both together, so this is mr square by 2 plus m by 2, mass is half, r square by 2 into omega prime. From here you will get the omega. Just look at the question, and then that will make it more clear. That will be more clear. That will be more important for you. Okay. So it comes 2 by 3 omega. This answer will be 2 by 3 omega. Okay. Next question is 2-3 more questions are there. Next question, please write. Question is given like this. There is a disk . There is a disk. This is O prime, and there is an insect here. Insect insect is crawling. The question is given. Question is, figure shows an insect at the rim of the disk. Figure shows insect at the rim of the disk that can turn about a frictionless axis. Means disk can turn about the frictionless axis. Initially the system is at rest. Initially the system is at rest. The insect crawls along the edge of the disk. Insect crawls along the edge of the disk. Insect crawls on the rim of the disk. So analyze the system. Question is so analyze the system. Again, question means it is a basically two bodies rotatory system. This is there. So you can see initially disk and the insect is at rest. So initially now it starts crawling. So the moment insect starts crawling, क्या होगा? Insects crawl क्यों होगा? Why anybody walks? Because of friction, static friction. So insects पे forward act में static friction act होगा, and in turn on the disk also in backward direction same static friction act होगा. Again it's a 3D. So you can just imagine it's a disk. यहाँ पे insect crawl हो रहा है. तो on insect the static friction forward, on disk it will be in backward direction. Okay. So analyze the system. Analyze the system meaning what? We have to see how we can solve the question if it is there. You can see one thing is that initially system is at rest. The moment insect starts crawling, the disk will also start rotating. Reason, you can see the disk pe static friction is going to act tangentially like this. Static friction will act like this, along this. So for this static friction there is a torque about the axis, torque about the hinge point. So this disk will start rotating like this and insect will crawl like this. So insect is crawling in forward direction, disk will start rotating in backward direction. I think are you getting this? If you go through, if you solve it by our force diagram, so this disk is going to rotate like this and this insect will move like this. Okay. So now if I take both in my system, so there will be a hinge force again. Okay. On insect there will be a normal reaction. Its mass, let's say mg. For disk there will be mass mg. Insect and static friction is there. If I take both in my system, n will be balanced by mg because insect is not moving vertical direction. This n0 will be balancing capital Mg. This static friction will balance each other because since I have taken both in my system, so static friction on the insect will be forward direction and static friction on disk will be in backward direction. So both will balance each other. What about torque? Again यहाँ पे system, again यहाँ पे since system पे अगर if I take both in my system, so this n0 will be balancing mg as well as small mg. Again इस यहाँ पे एक और force आ जाएगा. यहाँ पे n by the, since disk is applying n on the insect, so insect will also apply n in vertically down direction. So this n will be balanced by this n. If I take both in my system, this n will be balanced by this n, this fs will be balanced by this. this mg or this mg will be balanced by n naught. So if I take both in my system, energy conservation we can apply here, but we don't have the specific means the data is not given. Okay, so energy conservation can be applied. Why? Because static friction is doing work, okay, on the disk and on the insect. On both, static friction is doing work. So if we have a data, we can do this. Second, if I take both in my system, then mg or n naught here won't be impulsive because it's not a collision, it is just a crawling of an insect. So n naught and mg is an external force. So in vertical direction we cannot apply the momentum conservation, but in horizontal direction we can apply the momentum conservation. But we need a data. Next is third point we can have here. If I take torque about O, if I take this is my axis of disk is passing through O prime. So torque about O prime, about let's say this is center C. Torque due to N naught mg 0, torque due to Fs 0. Okay. And this will be the torque. The small mg will have a torque here. Small mg, because due to mg or n naught torque is 0, due to this n and this n, means n on the disk and these two will cancel each other. So this mg, the mg of the insect will be there. So due to that, torque will be there. So if I draw it again here, if I draw this, so let's say, so due to this mg mass of the insect, torque will be there. But mass of insect is how much? It's very, very small. So we can neglect this mg. So torque due to this mg can be neglected for doing the calculation. Okay. So here if I write, so when initial angular momentum is, so here we can write L initial equal to L final, because torque about O is 0, we have neglected the mass of insect. So here L initial will be what? So initially both are at rest. Finally, let's say disk is rotating in backward direction, so I of the disk into omega. So it is going in backward, it's a clockwise. Okay, so it is going like this, and for insect, let's say I of the insect into its omega, let's say omega 1 omega 2, it will be like this. So both in opposite direction. So we can here write, for when the insect starts moving, I can write moment of inertia of disk into its omega 1 equal to moment of inertia of insect into its omega 2. So this can be written both in opposite, so there will be a minus sign like this. So when there is a two bodies rotatory system, it is two bodies in a rotation. So when there is a two bodies rotatory system, we can follow this system. We can conserve the angular momentum without any just we have to keep I, the mass of mg, the mass of insect, the mass of person has to be 0, and that can be neglected actually. Okay, so just go through it. So we can apply, we can find the moment insect starts moving with certain angular velocity. So what is the angular velocity of the disk? We can find it like this. After this, you have to solve few questions are also there that I will be solving in next class. Now you have to solve 50 to 58 question number in SC Verma solved example. So page number is 198 question 50 to 58 you have to solve. Okay, so try this question. So this is all about angular momentum conservation. Go through this 2 or 3 times, that will make it more clear. And be safe, be at home, keep watching Milestone Academy channel. Thank you.